Hi everybody, today we are going to finish activity 24 with talking about lesson 24-3, which is tangent segments. So make sure you have your Springboard book open up to page 345, something to write with, and you might want a calculator. So today we're going to be talking about tangent segments and using those to solve problems. So let's look at this first picture here. The tangent segment to a circle from a point outside the circle are congruent. This is a theorem that we're going to prove here. Now, a tangent segment is a segment to a circle is part of a tangent line with one endpoint on the outside of the circle and the second endpoint at the point of tangency to the circle. So let's look at this picture here. Okay. So what they're saying here is we have this picture. So a tangent segment is a segment like this. So one point is outside the circle, your other endpoint is at that point of tangency. Okay, so BD is a tangent segment, but so is CD. Now this first theorem, okay, what they want us to prove basically is that DB, okay, is congruent to DC. Now, we're going to think about this as a little picture here on the next slide here of a picture of an ice cream cone. Okay. Now, when we have an ice cream cone, what we want is we want to make sure the worst thing that could happen with an ice cream cone is that your ice cream falls off, okay, hits the ground, no more ice cream for you. So think of our ice cream part as our circle. Okay. And think of the cone, okay, as being a tangent segment. So we have our point of tangency here and here, and then we meet here at the tip of our cone. Now, if we had a nice ice cream cone and we don't want our ice cream cone to fall off, then we want these to be nice symmetrical sides to our cone. Okay, so think of these problems as the ice cream cone problems, where we want these to be congruent or the same. So that way we have a nice symmetrical cone. Ice cream's not going anywhere. We'll be able to enjoy our treat. Okay. Now, I just put in this proof for you guys, but here's the proof from your book that shows you how we can actually prove that those tangent segments are congruent. Okay. So what we can kind of put in here is we have some triangles that we're going to make. We have a radii we could draw in from both points here to those points of tangency. So we know that all radii are congruent, right? So we can prove that those are congruent. We can also connect this point from A to D, and we can say that that is congruent to itself, reflexive property, which we've learned before. And don't forget from our previous lesson, anytime we have a radii to a tangent line, we do have right angles. Okay. So they do go through all this. Now we can prove that those two triangles here are congruent, okay, by using our HL theorem, hypotenuse leg, which we haven't used in a while. But remember, in a hypotenuse leg, if we know the hypotenuse and one leg of our right triangle is congruent, then we can prove triangle congruence. So then by CPCTC, we can prove that those tangent segments are actually congruent to each other. Okay? So we're going to use this to solve some problems on the next page. So the theorem here is that anytime you have two tangent lines coming from one point, so in this problem, point D, we have two tangent segments, those segments will always be congruent. Okay? So I proved it here with this proof from the book. So now we can always use that. So let's go to the next slide here. Look at problem 2. Okay. We have in this diagram, RT is 12 centimeters. Let's label that. Okay. RH is 5 centimeters. MT is 21. Okay. We need to find the missing length for all the other segments, preferably and most importantly RM. So this is what we would call a walk-around problem. We're basically going to be using deductive reasoning to find all of our missing segments. Now, we have points of tangency at H, A, and D. Now, since those are going out to these points outside the circle, we can use that theorem and say that those 2 points, RH and RD, are congruent. Same thing with TH and TA are congruent. And lastly, AM and MD are congruent. Okay. So here's what we can do. If we know, okay, that RH is 5, then so is RD, because they're congruent segments. Also, if this whole side length is 12 and this side is 5, what does that make HT? Well, if we subtract that, 12 minus 5 would be 7. So we know that this is 7. And then that congruent segment is also 7. Okay. Now, if this whole length, MT, is 21 and AT is 7, well, that makes AM 14. And that makes this segment 14. So now that we know all of our little segments, what's the length of RM? Well, 5 plus 14, RM is 19. Okay, so again, we call this a walk-around problem because we're literally starting at one point and walking our way around the problem to solve all those missing sides. So using subtraction and that idea that our tangent segments are going to be congruent. Okay, let's look at part B here. Part B says if OH is 4 centimeters, maybe let's draw OH in here. Okay, what's the length of OT? Here's OT. We'll draw that in. Now this is going to get a little messy, so I might do it on the side here. But don't forget from our previous lesson that we did learn that a radii to a tangent line does form, okay, a right angle. So this would be a right triangle here. So let me pull this out so we can actually see this a little better. Okay, so here's that same triangle. I'm just doing it on the side here because it's going to get a little messy with all this writing. So they said that OH was 4. Now from our picture, we learned that HT was 7. So how do we find OT? Well, if we have a right triangle, we just have to do a little Pythagorean theorem here. So let's set it up. We have 7 squared plus 4 squared is equal to x squared. Let's see. 7 squared plus 4 squared. Okay, we get 65. Okay. And then to find that, we just have to square root, right? So let's just get the decimal for this right now. Square root of 65. We have 8.06. So OT is about 8.06. Okay. So don't forget our previous theorem about our tangent lines and our radii, and we can always include that now with our new theorem about these chords. Okay. We're just going to kind of finish off with some problems here at the bottom, 4 and 5. So let's look at 4. It says using the diagram in number 2. So I just recopied it on my page. So if you want to pause here and do that for yourself and redraw that diagram, that works. But it's another walk around problem. We have RM is 40. Okay. AM is 32. Name the other measurements you can find, and then find those measurements. Okay, so let's fill in our congruent parts. So anything that comes from a point to a point of tangency forms those congruent segments. So let's fill in what we can figure out here. So let's see, we can know, since this is 32 and it's congruent to DM, we know DM is also 32. Okay. Well, then I can use subtraction then to find RD. Well, RD then would have to be what? 40 minus 32 is 8. So that makes RH also 8. But that's actually all that I can find. Okay, and I don't have enough information to find the TH or AT since we don't know the whole length of MT and we don't know what that, or the full length of RT. So really, those are the only other measurements I could find with this given information. Okay. All right, last problem I'm going to have you guys do is number 5. So in the diagram, NM and QN are tangent to circle P. So if we have our tangent segments, we can prove that we already know that those two lines then are congruent. Okay, it has a radius of 5. Now if that's 5, then this other radius, because all radii are congruent, is also 5. And it says MN is 12. So in A, they want you to find what QN is. So what's the length of QN? Hopefully you realize that those are your two congruent parts, so they have to be the same. So that was also 12. Okay, and now lastly, they want us to find PN. So let's draw on this line PN here. Now remember, you have right triangles. So you have 12, 5. What's the length of your hypotenuse then? What is PN? So I'm going to have you guys set that up, solve for PN, and then we are done with this lesson. Okay, if you did it correctly, you should have got that PN is 13. Now you could set it up using Pythagorean theorem. 5 squared plus 12 squared equal to x squared. Or if you remembered, 5, 12, 13 is a Pythagorean triple. So if you remembered your triples, then you could solve this a lot faster. But that is all of our properties using tangent segments. So the segments from the same point to your lines of tangency in a circle are always congruent. But again, don't forget that a radii in a tangent segment form a right angle as well.